All right, hey everybody. So I want to remind you where we left off our last video because it will sort of motivate us going forward. So we have been looking at the normal curvature of a surface at a given point, right? And so at any point on our surface, at a point P on our surface S, the normal curvature was computed first by taking a curve through the surface at that point and looking at the curvature of that curve and how it compared to the normal direction of the surface. But then we were able to see that it really just boiled down to the direction that that curve was going, right? So if the curve was going in a certain direction when it passed through the point, that was enough to determine the normal curvature. And so we figured out that at any given direction we want to look, we can calculate the normal curvature in that direction. Now with a surface, of course, we have 360 degrees worth of directions to explore, but we could theoretically check all of them, right? Or come up with a function for all of them and be able to have a pretty good understanding of what our surface looks like as far as how it's curved at our point in any given direction, right? And of course, the key to doing this was our second fundamental form because we found that the normal curvature was equal to the second fundamental form. So with that in mind, if we were to check every direction in our complete 360 degrees of movement ability on that surface, can we find the extreme values of curvature? In other words, can we find the biggest curvature? Can we find the smallest curvature? So can we find the direction in which the surface is as curved as possible in this direction? And can we find the direction in which the surface is as sort of curved in the opposite direction as possible? So our two extremes, can we find them? Turns out the answer is yes, and being able to find it is really a really nice blend of linear algebra theory and calculus 3 theory. And the end results are really, really valuable to us. So it's a really exciting thing to be able to talk about. We'll be a little hand-wavy in some of the Calc 3 or linear algebra deeper details, but I'll point out where we're being hand-wavy, or I think it'll be clear. First, our goal is to try to find maximum and minimum values of a curvature expression, right? And so we are trying to find, maybe to set it up nicely, a unit vector in our tangent plane. So this is a vector w, and we'll represent it as the expression a comma b, with the understanding that this really means, oh, let me choose a different color. That color's already in use. Here we go. With the understanding that a comma b really means this is a x sub u plus b x sub v, right? So our basis, as has been when we're working in tangent planes, will continue to be x sub u and x sub v, and we'll write our vectors in this vector notation with that understanding. So can we find a vector w that optimizes our second fundamental form, right? In other words, finds maximum or minimum values, finds extreme values for our second fundamental form. And that boils down to, or that simplifies down to this equation involving our 4 entries in our second fundamental form. So we're trying to find maximums and minimums of this equation subject to a constraint that the only vectors we want to think about are our unit vectors. In other words, vectors w for which the length is equal to 1. And the length, right, is the square root of the first fundamental form. So we're really trying to find vectors subject to a constraint that our first fundamental form squared is equal to 1. So just our first fundamental form is equal to 1 when we plug in w with w. And that simplifies down to this blue equation down here, right? So what are we doing? We're trying to find values of a and b that optimize this equation subject to this constraint. And for those of you who have looked a little bit at multivariable calc, you can recognize this is an optimization problem with a constraint. This is the realm of Lagrange multipliers. So we can use Lagrange multipliers to try to find optimum solutions to this equation with this constraint. So Lagrange multiplier work not being shown here, right? That's for those of you who are interested and have seen a little bit of that in multivariable. calc, but the end result is that, yes, we should be able to find two vectors and corresponding directions. So I'll, both vectors I'll denote as AB and both directions. I'm sorry, there's a small typo here. Let me fix this. This should be two vectors. Those are our directions, AB, and this should say values, right? Values, lambda. And these equations should satisfy this expression here, right? This is our optimization. This is what our optimization problem is telling us. And so it turns out that those values lambda will be our biggest and smallest curvatures. We'll get to that in a moment. First, let me simplify this down a little bit, and we can talk a little bit linear algebra here for a second. Right? The equation that we're trying to find solutions for, we're trying to find AB and then values lambda that satisfy this equation. This is our second fundamental form. This is our first fundamental form. But our first fundamental form is invertible, right? So I can multiply by the inverse and move that over here. So we get the inverse of the first fundamental form times the second fundamental form times AB equals lambda times AB. In other words, this is a eigenvector eigenvalue problem, right? Which is why we're using the letter lambda for the moment. On top of that, the first fundamental form inverse times the second fundamental form has another name. That is just our differential of our Gauss map, right? By the Weingarten equation, this times this was equal to this. So what we're really trying to do here, or what the theory says that these optimum solutions will be, are going to be the eigenvectors and eigenvalues of our Weingarten equation, right? Or our Weingarten, I should say, the eigenvalues and eigenvectors of our differentials, right? As given by the Weingarten equation. So the solutions that we get are two solutions, right? Which I could call lambda 1 and lambda 2. And then we get corresponding directions, that's W1 and W2. And these are going to be called the principal curvatures and the principal directions of our surface at this given point. And now it's worth changing our notation slightly, right? Because we were looking for eigenvalues, we use the lambda, the classic lambda, but our principal curvatures will often instead be called kappa 1 and kappa 2, right, as our traditional curvature letter. So kappa 1 and kappa 2 are our principal curvatures, giving us the maximum value and minimum value of curvature at a given point, as well as the principal directions that they point in. Furthermore, there is an amazing fact, I'll call it an amazing fact, it's actually a deep linear algebra fact, that W1 and W2 will be perpendicular to each other. So not only will we get principal directions, a direction of maximum curvature and a direction of minimum curvature, but at every single point, they will always be perpendicular to each other. This amazing fact is often called the spectral theorem, and it pops up in different forms in different locations throughout linear algebra and higher mathematics. Here, this version of the spectral theorem is saying that these two principal directions will be perpendicular to each other. All right, so I want to end this video just by jumping way, way back to one of our earlier pictures. Here we go. And we had talked a little bit, this is from several videos ago, we had talked about how curvature, or how surfaces could look different at different points depending on how they were curved. And I named these four kinds of points, the elliptic, hyperbolic, parabolic, and planar points. With the introduction of our principal curvatures, I'm now in a position to tell you what makes an elliptic point an elliptic point. And, similarly for the others. So what makes an elliptic point is that both of my principal curvatures, kappa 1 and kappa 2, will have the same sign. They will either both be positive or both be negative, depending on if we're sort of sitting in a bowl or sitting sort of on top of a upside down bowl, right? But that would be an elliptic point. A hyperbolic point will have one of our principal curvatures be greater than 0 and one of our principal curvatures be less than 0. A parabolic point will have exactly one of our curvatures being 0 the other one being either positive or negative. And a planar point will have both principal curvatures being equal to 0. So those identifications are coming from our principal curvature formulation. Awesome.